Welcome to this coding walkthrough. In this session, we'll explore problem number 76, minimum window substring, a classic problem that challenges your skills in string manipulation and algorithm optimization. Let's dive into the problem details and break it down step by step. This problem challenges us to find the smallest substring in the string S that contains all the characters of string T, including duplicates, in any order. If such a substring doesn't exist, we simply return an empty string. For example, if T contains the character A twice, the substring in S must also include two occurrences of A to be valid. The input constraints specify that both S and T are strings of lengths up to 10,000, and they consist only of English letters, both uppercase and lowercase. The result should be the smallest valid substring of S, and if there are multiple substrings of the same minimum length, we return the one that appears first in S. This means the solution must carefully balance correctness and efficiency, given the potentially large input sizes. For example, let's consider the case where S is ATABECO and T is ABC. The output here is bank because it is the smallest substring of S that contains all the characters in T, specifically A, B, and C. While there are other substrings in S that include these characters, such as ATABEC or CodeBank, they are all longer than bank. Now, in a simpler case where both S and T are just the string A, the output is A because S already contains exactly what T requires. These examples illustrate how the solution must account for both the size and content of the substrings to determine the result. In contrast, consider the case where S is A and T is AA. Here, the output is an empty string. This is because T requires two occurrences of the character A, but S only contains one. Since it's impossible to satisfy the condition that all characters of T must appear in a substring of S, the result must be empty. This highlights the importance of ensuring that the frequency of each character in T is fully met by the substring in S in order for it to be considered valid. Now let's address some important constraints and edge cases. First, if the length of T is greater than the length of S, it's immediately clear that no valid substring can exist, so the result is always an empty string. Similarly, if T contains any character that doesn't appear in S, the output is also an empty string because it's impossible to satisfy the inclusion requirement. Additionally, since both S and T can have repeated characters, the solution must account for the exact frequency of each character in T. Finally, remember that the case of letters matters, so A and A are considered distinct characters. These edge cases and constraints guide the logic and efficiency of the solution required for this problem. To solve the minimum window substring problem, one approach we could consider is the brute force method. The intuition here is straightforward. We generate all possible substrings of the input string S and then check each one to see if it contains all the characters of the string T with the required frequencies. To break it down, we would first generate these substrings, then count the characters in each, compare them with the frequency count of T, and finally keep track of the smallest substring that meets the condition. However, while this approach is conceptually simple, it is computationally expensive. Generating substrings alone has a quadratic time complexity, and validating each substring adds another layer of computation. As a result, this method becomes impractical for larger inputs, making it clear that we need a more efficient solution to handle real-world scenarios effectively. A more efficient approach to this problem is the sliding window technique. The key idea here is to use two pointers to represent a dynamic window that expands and contracts as needed, allowing us to avoid generating all substrings. By maintaining a frequency count of characters in T in the current window, we can determine when the window contains all required characters. Starting with the right pointer, we expand the window to include new characters until it satisfies the condition. At that point, we begin contracting the window using the left pointer to minimize its size while still ensuring it remains valid. This dynamic adjustment allows us to efficiently track the smallest valid window and update the result as necessary. This technique is both logical and computationally efficient, making it a significant improvement over brute force. The sliding window approach achieves a time complexity of O, m plus n, where m is the length of S and n is the length of T. This efficiency comes from the fact that both pointers traverse the string S at most once, and operations like updating the frequency map are performed in constant time. In terms of space, we use O, n, for the frequency map of T. The advantages of this method are clear. It avoids unnecessary checks, dynamically adjusts the window size, and is scalable for larger inputs. Alternative strategies, such as using a hash map with 2 passes or leveraging binary search, can also be considered but come with additional complexities. The hash map approach, for instance, involves overhead in managing the character counts, while binary search requires extra computation for validation and is less intuitive. Overall, the sliding window technique stands out as both efficient and elegant. The sliding window approach is the chosen strategy for this problem because it strikes the perfect balance between simplicity and efficiency. Unlike brute force, which is computationally expensive, or alternative methods like binary search, which add unnecessary complexity, the sliding window approach optimally handles the problem. By dynamically expanding and contracting the window, it ensures that we minimize the computation while maintaining clarity in the implementation. However, like any method, there are trade-offs to consider. While brute force is simple, it is too slow for large inputs. Sliding window, on the other hand, is efficient but requires careful handling of edge cases, such as empty strings or characters in T that are missing from S. Ultimately, sliding window is the best choice due to its linear time complexity and minimal space usage, making it highly suitable for competitive programming and real-world applications where performance is a priority. The problem asks us to find the smallest substring in string S that contains all characters of string T, including their frequencies. If no such substring exists, we return an empty string. To solve this efficiently, we use a sliding window approach combined with hash maps. The intuition here is that instead of checking every possible substring, which would be computationally expensive, we dynamically adjust a window over S to find valid substrings while maintaining the condition of containing all characters in T. This is achieved by using hash maps to track character frequencies. To begin, we initialize 2 hash maps, T_count, which holds the frequency of characters in T, and window_count, which tracks the frequency of characters in the current window of S. We also set 2 pointers, left and right, both starting at the beginning of S. Additionally, we use a variable required to represent the number of unique characters in T that need to be fully matched, and another variable form to track how many of those characters are currently matched in the window. Finally, we set up a result variable, min_window, to keep track of the smallest valid window found so far, storing its length and indices for easy reference later on. Once the data structures are initialized, we populate T_count by iterating through the characters in T and recording their frequencies. Using this, we set required to the number of unique characters in T_count. Next, we expand the window by moving the right pointer from the start of S to its end. With each step, we add the character at the right pointer to window_count and update its frequency. If the frequency of this character in window_count matches its frequency in T_count, we increment formed. When formed equals required, it means the current window contains all characters of T. At this point, we begin contracting the window by moving the left pointer. For each step, we check if the current window is smaller than the previously recorded min_window, and if so, we update min_window. Then, we remove the character at the left pointer from window_count by decrementing its frequency. If this causes the frequency of the character in window_count to drop below its frequency in T_count, we decrement formed. This process of expanding and contracting continues, ensuring that we explore all possible valid windows while keeping track of the smallest one. The process continues as the right pointer increments, expanding the window and checking for validity. Each time the window satisfies the condition of containing all characters of T, we attempt to contract it by moving the left pointer inward. This dynamic adjustment ensures that we only process each character at most twice, once when expanding and once when contracting. After iterating through the entire string S, we check the min_window variable. If it remains unchanged, we return an empty string, indicating no valid window was found. Otherwise, we return the substring of S defined by the indices stored in min_window. This approach is efficient because it avoids brute forcing all substrings and instead uses a targeted search strategy. The sliding window technique, combined with hash maps, allows us to efficiently manage the conditions for a valid substring while dynamically adjusting the window size. There are several key insights about this algorithm that make it efficient. First, the sliding window approach ensures that we only scan through the string S twice, significantly reducing the time complexity compared to generating all substrings. Second, hash maps provide constant-time operations for checking and updating character frequencies, making it easy to verify if the current window satisfies the condition of containing all characters in T. The dynamic size of the window allows us to minimize unnecessary checks and focus only on valid substrings. To implement this, we use three main data structures. Hash maps, T_count and window_count, track the frequencies of characters in T and the current window of S, respectively. Two pointers, left and right, manage the boundaries of the sliding window. Lastly, the result tuple, min_window, keeps track of the smallest valid window found, storing its length and indices for efficient retrieval. These components work together to ensure the algorithm is both efficient and easy to implement. Handling edge cases is crucial to ensure the algorithm produces correct results across all input scenarios. For example, if the length of T is greater than S, it's impossible to find a valid window, so we immediately return an empty string. Similarly, if no matching substring exists, the algorithm will return an empty string after completing its iteration. For cases where multiple valid substrings of the same length are found, the algorithm naturally returns the one that occurs first, as the right pointer expands sequentially. When T contains duplicate characters, such as T equals AAB, the window must satisfy the frequency condition for all characters, meaning it must contain at least 2 AS and 1 B. The complexity analysis further highlights the efficiency of this approach. The time complexity is O, n plus m, where O, m, accounts for populating T_count and O, n, represents the sliding window traversal. For space complexity, we use O, m, for T_count and O, n, for window_count, making it dependent on the sizes of T and S. The pseudocode implementation ties all these concepts together. We start by importing the counter class from Python's collections module to easily handle character frequency counts. After checking for edge cases where either S or T is empty, we initialize T_count using counter to store the character frequencies of T. We also create an empty dictionary for window_count. The variables required, formed, left, right, and min_window are initialized to manage the logic of the algorithm. The right pointer iterates through S, updating window_count and checking if the condition for forming a valid window is met. Once a valid window is found, the left pointer begins contracting the window while checking if it's the smallest valid one. The process continues until all characters in S are processed. Finally, the function returns the smallest valid substring or an empty string if no valid window exists. This implementation ensures clarity, efficiency, and correctness by adhering to the principles of the sliding window approach. Here, we start by importing the counter class from the collections module, which will help us count the frequency of characters in the string T. Inside the solution class, the min_window method is defined to find the minimum window in string S that contains all the characters in string T. The first step is a base case check. If either S or T is empty, we immediately return an empty string, as no valid window can exist. Next, we use the counter to calculate the frequency of each character in T and store this in T_count. The variable required is set to the number of unique characters in T. Then, we initialize pointers left and right for our sliding window, along with a variable form to track how many unique characters in the current window meet their required frequency. Additionally, we create a dictionary window_counts to track the frequency of characters in the current window and a tuple ANS to store the smallest window found so far. The tuple consists of the window length and the indices of its start and end. Now, we begin iterating over S using the right pointer. Each time, the character at the right pointer is added to window_counts, and if this character meets its required frequency in T_count, we increment form to reflect that this character is now satisfied in the current window. When all required characters are satisfied, meaning formed equals required, we try to shrink the window from the left to find the smallest valid substring. Inside this inner loop, the character at the left pointer is examined, and if the current window is smaller than the previous best, the ANS tuple is updated with the new window size and indices. Then, the character at the left pointer is removed from window_counts, and if this causes the count of that character to drop below its required frequency in T_count, we decrement form to indicate that the window is no longer valid. The left pointer is then moved one step to the right to continue contracting the window. After exiting the inner loop, the right pointer is incremented to expand the window and continue exploring the string S. Once the loop finishes, the method checks if a valid window was found by examining the length stored in ANS. If no valid window exists, an empty string is returned. Otherwise, the substring of S corresponding to the indices in ANS is returned as the smallest valid window. To begin our Java implementation of the minimum window substring problem, we start by checking for edge cases. If either string S or T is null, empty, or invalid, we return an empty string as there's no valid window to find. Next, we initialize a hash map, tcount, to store the frequency of each character in the string T. This map will help us track what characters are required in the sliding window. We then calculate the total number of unique characters in T by using the size of this map, which we store in the variable required. We initialize two pointers, left and right, both starting at the beginning of the string S, to define our sliding window. Additionally, we create another map, windowCounts, to track the frequency of characters currently in the window. To keep track of the smallest valid window, we use an array ANS where the first element represents the window length and the other two elements store the indices of the window. Finally, we enter a while loop that iterates as long as the right pointer is within the bounds of the string S, expanding the window by adding characters one at a time. Within the loop, each character at the right pointer is added to the windowCounts map, updating its count. If this character is also in tcount and its frequency in windowCounts matches that in tcount, we increment the formed variable. This variable tracks how many unique characters in the current window meet their required counts. Once formed equals required, it indicates that the current window contains all necessary characters from T. At this point, we attempt to contract the window by moving the left pointer inward. For each iteration, we check if the current window is smaller than the smallest one found so far. If it is, we update the ANS array with the new window size and indices. As we shrink the window, we adjust the frequency of the character being removed in windowCounts. If this adjustment causes the frequency to drop below the required count in tcount, we decrement formed, indicating the window is no longer valid. The contraction process continues until the window no longer satisfies the condition, at which point we expand the window again by incrementing the right pointer. Once the loop finishes, we check the ANS array to determine if a valid window was found. If the smallest window length remains the initialized value of integer.max_value, it means no valid window was found, and we return an empty string. Otherwise, we use the indices stored in ANS to extract and return the substring from S that represents the minimum window. This completes the implementation, efficiently finding the smallest substring in S that contains all characters of T, while handling edge cases and ensuring optimal performance with the sliding window approach. We start by looking at the example where S is ADABECO and T is ABC. First, we initialize all the variables we need for the sliding window approach. The T_count variable is a counter that keeps track of the frequency of each character in T. Since T contains a B and C, each with a frequency of 1, T_count is 1, B1, C1. The required variable is the number of unique characters in T, which is 3. Next, we initialize the pointers left and right to 0 to represent the current window, and form to 0 to track how many characters in the current window meet the required frequency from T. We also set up an empty dictionary, window_counts, to count characters within the window, and ANS to store the size and boundaries of the smallest valid window we find. Now, we expand the right pointer. At right equals 0, the character is a. Adding it to window_counts gives a 1, and since this matches the frequency in T_count, we increment formed to 1. At right equals 1, the character is D. Adding it updates window_counts to a 1, D1, but since D is not in T, formed remains 1. At right equals 2, the character O is added, making window_counts a 1, D1, O1, with no change to formed. At right equals 3, we encounter B, and adding it updates window_counts to a 1, D1, O1, B1. Since B matches its count in T, we increment formed to 2. Finally, at right equals 4, the character E is added to window_counts, but it does not affect formed as E is not in T. At right equals 5, the character C is added to the window, updating window_counts to a 1, D1, O1, B1, E1, C1. Now, C matches its count in T, so we increment formed to 3. At this point, formed equals required, meaning the current window from left equals 0 to right equals 5 contains all the characters in T with the required frequencies. This is a valid window, so we check its size, which is 6. Since this is the smallest window we've seen so far, we update ANS to 605. Now, we try to shrink the window from the left. Removing it reduces its count in window underscore counts to 0, which is below its required count in T underscore count. As a result, we decrement form to 2, and the window is no longer valid. Next, we continue expanding the right pointer. This process of expanding the right pointer and shrinking the left pointer continues until right reaches the end of the string. When the algorithm completes, the smallest valid window found is from left equals 9 to right equals 12, with a length of 4. The substring corresponding to this window is bank, which is our final output. In the second example, S is at and T is AA. During initialization, T underscore count becomes 2 because it appears twice in T. The required variable is set to 1 since there is only one unique character in T. We also initialize left and right to 0, form to 0, and empty window underscore counts dictionary, and ANS as ANF, none, none. When we begin expanding the right pointer, at right equals 0, the character it is added to window underscore counts, making it 1. However, the count of it in the window is still less than the required count in T underscore count, so formed remains 0. Since there are no more characters in S to process, and formed never equals required, we conclude that no valid window exists for this case. The output, therefore, is an empty string. In the third example, S is AA and T is AA. For initialization, T underscore count becomes 2 since it appears twice in T. The required variable is set to 1 because there is only one unique character in T. As before, we initialize left and right to 0, form to 0, window underscore counts as an empty dictionary, and ANS as ANF, none, none. When we start expanding the right pointer, at right equals 0, the character it is added to window underscore counts, making it 1. However, the count of it in the window is less than the required count in T underscore count, so formed remains 0. At right equals 1, we encounter another which updates window underscore counts to 2. Now, the count of it in the window matches its required count in T underscore count, so we increment formed to 1. At this point, the window is valid since formed equals required. Once a valid window is found in this example, we calculate its size, which is 2, and update ANS to 2, 0, 1. To explore smaller windows, we try to shrink the window from the left by removing a. This reduces the count of a in window underscore counts to 1, which is below the required count in T underscore count. As a result, formed is decrement to 0, and the window is no longer valid. Since there are no more characters to process, the smallest valid window remains from left equals 0 to right equals 1. The substring corresponding to this window is AA, which is the final output for this example. Time complexity begins with the initialization phase, where we compute the frequency of characters in the string T using a counter object. This operation takes time since we iterate through the entire string T once. Additionally, setting up pointers and variables like left, right, and other constants requires time. Next, we expand the right pointer as part of the sliding window technique. Here, the outer while loop ensures the right pointer traverses the entire string S, meaning it executes at most n times. Within this loop, updates to the window underscore counts dictionary and any condition checks are constant time operations, or O1. Finally, we contract the left pointer when the current window is valid. The left pointer similarly traverses the entire string S, moving it most n times. Each contraction involves constant time updates and checks, which makes the inner loop efficient as well. Now, considering the overall traversal of the string, both the right and left pointers move independently, and each can traverse the string S entirely, but never more than once. This means the total number of operations for expanding and contracting the window is n. When we combine this with the initialization phase, the overall time complexity becomes n plus m. The m comes from the initial setup of the character counts for T, and the n arises from the sliding window traversal. Moving on to space complexity, let's analyze the storage requirements. First, we have the counter object T underscore count, which keeps track of the frequency of characters in T. This requires OK space, where K is the number of unique characters in T. Then, we have the window_counts dictionary, which stores the frequency of characters in the current window of S. In the worst case, where all characters in S are unique, this dictionary could require O(n) space. Additionally, we use a few variables like left, right, formed, required, and ans. These are simple scalar values, so they only consume O(1) space. When we combine all these factors, the total space complexity becomes O(n) plus k. The O(n) comes from the space needed for the window_counts dictionary, and the O(k) comes from the counter object for T. To better understand performance, we can look at the best, average, and worst case scenarios. In the best case, if all the characters of T are located near the beginning of S, the algorithm quickly finds a valid window. However, even in this scenario, the sliding window still traverses S, so the time complexity remains O(n) plus m. In an average case, the algorithm performs similarly, requiring O(n) for the sliding window and O(m) for initialization. Finally, in the worst-case scenario, where the desired substring spans most of S, both pointers traverse the string entirely. Despite this, the time complexity is still O(n) plus m, due to the efficient linear traversal. To highlight the efficiency of the sliding window approach, let's compare it to a brute force method. A naive solution would involve generating all substrings of S and checking each one for validity against T. Generating all substrings of S would require O(n) squared time, and verifying each substring would take O(m), resulting in a time complexity of O(n) squared asterisk m. In terms of space, brute force uses O(1), as no additional data structures are involved. In contrast, the sliding window approach significantly reduces the time complexity to O(n) plus m, by avoiding the generation of all substrings and leveraging direct traversal. The trade-off is a slightly higher space complexity of O(n) plus k, but this is a reasonable cost for the substantial improvement in time efficiency. Overall, the sliding window technique is far more practical and scalable for large inputs. Finally, let's solidify the time complexity with a mathematical proof. The outer loop, which corresponds to expanding the right pointer, runs O(n) times as the pointer traverses the string S. Similarly, the inner loop, which contracts the left pointer, also runs O(n) times at most. These loops alternate rather than nest, so their combined operations are linear, or O(n). Within these loops, operations such as dictionary updates and condition checks are constant time, or O(1). Therefore, the total time complexity is O(n) plus m, where the O(m) accounts for the initialization phase. For space complexity, the dominant factors are the dictionaries T_count and window_counts, which require OK and O(n) space respectively. Combining these, we get O(n) plus k for space usage. In summary, the sliding window approach achieves linear time complexity relative to the input sizes, making it an efficient and scalable solution compared to the quadratic time complexity of the brute force method. When solving the minimum window substring problem, there are a few common mistakes to watch out for. First, not handling edge cases can lead to incorrect results or runtime errors. For example, if the string T is longer than S, it's impossible to find a valid substring, so your algorithm should return an appropriate result, such as an empty string. Similarly, failing to handle empty input strings can break your solution. Next, an incorrect sliding window implementation can cause issues. If you don't properly update the window size or character counts when expanding or contracting the window, your program might miss valid substrings or produce incorrect results due to incomplete character tracking. Another mistake is using inefficient character matching techniques, like nested loops, to check if the current window contains all characters of T. This approach significantly increases time complexity to O(n) squared, or worse, which can cause timeouts for larger inputs. Instead, efficient data structures like hashmaps should be used to track character counts dynamically. Another common pitfall is ignoring case sensitivity or character types. Some problems may involve uppercase letters, digits, or special characters, so assuming all inputs are lowercase letters can lead to an incomplete solution. Always verify the constraints of the problem before proceeding. Additionally, premature optimization can be counterproductive. Overcomplicating the solution with unnecessary optimizations before ensuring correctness often leads to confusion and bugs. It's better to start with a clear and correct approach, then optimize for performance only if needed. This helps maintain clarity in your code and ensures you're addressing the problem requirements effectively. To perform well in an interview setting, it's essential to understand sliding window patterns. Many substring problems rely on variations of this technique, so practice defining clear rules for adding and removing elements during window expansion and contraction. Efficient character tracking is also critical. Using hash maps or frequency arrays allows you to update and check character counts in O(1) time, which is essential for maintaining an overall O(n) time complexity. Additionally, clear communication is key. When explaining your approach, articulate your thought process, especially how you're narrowing down the window and ensuring both correctness and efficiency. Finally, always test edge cases. Ask clarifying questions about inputs like empty strings, single character inputs, or duplicate characters to ensure your solution handles all scenarios. For related practice, consider problems like finding permutations in a string, finding the longest substring without repeating characters, or finding all anagrams in a string, which all use similar techniques. Now, let's explore some alternative approaches to solving the problem. One option is the brute force method, where you generate all substrings of S and check if each one contains all characters of T. While simple to implement, this approach is highly inefficient, with an O(n) cubed complexity due to the time required for substring generation and character matching. A more efficient solution is the optimized sliding window approach. By using 2 pointers and a hash map to dynamically track character frequencies, you can expand and contract the window as needed, achieving O(n) complexity. However, this requires careful implementation to handle edge cases and maintain accurate character counts. Another approach is combining binary search with the sliding window technique. Here, you perform a binary search on the substring length and use the sliding window to check feasibility. This has an O(n) log m complexity, where m is the size of the search space. While this method can be effective, it's more complex to implement and may not always outperform a direct sliding window approach depending on the input size. Thanks for joining this walkthrough. We hope you gained valuable insights into solving the minimum window substring problem efficiently. Stay tuned for more problem breakdowns, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!